On March 11, 2011, 16 minutes after the most powerful earthquake in Japan's recorded history finally stopped shaking, something happened that no scientist on the planet expected, and no scientist on the planet noticed. Every GPS station across the entire country of Japan, from the northern island of Hokkaido all the way down to Kyushu in the south, a stretch of land 1,800 miles long, registered the exact same thing at the exact same instant. The whole country lurched eastward, together, uniformly, as if some invisible hand had reached down and nudged an entire nation a few millimeters sideways all at once. There was no earthquake at that moment, no aftershock, nothing on any seismograph that would normally explain a sudden shift in the ground. And so, for over a decade, that strange, uniform lurch sat quietly buried inside an ocean of data from one of the most catastrophic natural disasters of the 21st century. Dismissed, ignored, assumed to be noise, a wrinkle nobody had the time or the reason to chase down while the rest of the world was mourning 20,000 lives and watching a nuclear crisis unfold at Fukushima. Imagine, for a moment, what that day actually looked like on the ground. Buildings still, swaying from the strongest shaking Japan had experienced in its recorded history. Sirens wailing along the coastline as a wall of water raced toward towns that had only minutes to evacuate. Emergency broadcasts, power failures, a nuclear plant beginning to fail at Fukushima. In the middle of all of that chaos, a network of GPS receivers scattered across the country kept doing exactly what they were built to do, quietly, continuously logging their own precise position in space, unaffected by sirens or panic or headlines, simply recording, second by second, exactly where the ground beneath them actually sat. Nobody was watching those numbers in real time for anything as subtle as a 5 mm shift. There was a nation to save. First, the data simply waited patiently for someone to come back to it years later with the right question. But one scientist couldn't let it go. And when she finally figured out what had actually happened, the answer was so strange that it rewrote what an earthquake is even capable of doing to this planet. Because what moved the entirety of Japan that day, scientists have now confirmed, wasn't the earthquake itself. It was an echo of that earthquake. A wave of seismic energy that had traveled 3,600 miles straight down into the earth, slammed into the molten metal core of our planet, bounced back up like a ball thrown against a wall, and returned to the surface 15 minutes later, carrying enough force to permanently shift not one, but 4 separate tectonic plates. Something that, by every rule seismology thought it understood, should have been physically impossible. By the end of this, you'll understand exactly why a signal that dissipated into the deepest, hottest, most crushing layer of our planet somehow came back out the other side with enough power left to move a country, and why that single, overlooked wiggle in 15th earthquakes on Earth actually behave. If you're new here, hit subscribe, because we go looking for exactly this kind of thing, the moments when a well-understood event turns out to be hiding something nobody thought to look for. To understand why this discovery is so unsettling to the people who study earthquakes for a living, you first have to understand something about how we ever learned what's hiding beneath our feet in the first place. Everything we know about the deep interior of this planet, the fact that it has a solid inner core wrapped in a molten outer core, all of it buried beneath a thick mantle of slowly flowing rock. We learned almost entirely by listening to earthquakes. Nobody has ever drilled anywhere close to the core. The deepest hole ever bored into the earth barely scratches 7.5 miles down, a fraction of a percent of the roughly 3,900 miles separating the surface from the center of the planet. Instead, generations of seismologists built their picture of Earth's interior the same way a doctor reads an ultrasound, or the way a bat navigates in the dark, by sending waves through something opaque and listening carefully to how they come back changed. It was exactly this kind of listening that, in the 1930s, led a Danish seismologist named Inge Lehmann to first prove that Earth's core wasn't a single uniform ball, but had an inner, solid layer nested inside an outer, liquid one. A discovery made entirely from the way seismic waves bent and reflected as they passed through or bounced off the planet's hidden depths. Every subsequent decade of seismology has added detail to that same basic method. Send a wave down, watch what comes back, and let the physics tell you what's down there that no human eye will ever directly see. To understand why what happened in Japan mattered so much, you first have to understand what actually happens when the ground shakes. An earthquake releases its energy in the form of seismic waves, vibrations that radiate outward from the point of rupture in every direction at once, the way ripples spread outward from a stone dropped into a pond, except these ripples move through solid rock, and some of the fastest ones travel straight down deep into the planet's interior. Seismologists have known for decades that the largest of these waves don't just fade out somewhere in the mantle. Some of them keep going, all the way down to the boundary between Earth's rocky mantle and its liquid metal outer core, roughly 1,800 miles beneath the surface. And when they hit that boundary, they can actually bounce, reflecting back upward the same way a sound wave bounces off a wall or the way light reflects off the surface of water. Seismologists even have a name for this specific kind of reflected wave. They call it a CS, shorthand for a shear wave that travels down, reflects off the core, and travels back up as another shear wave. It's a well-documented, thoroughly cataloged part of how energy moves through this planet, studied for the better part of a century as a tool for mapping the depth and shape of the core itself. Researchers had recorded countless examples of SCS waves arriving at seismic stations around the world after large earthquakes, faint but detectable, confirming exactly where that mantle core boundary sits and how sharply defined it is. What nobody had ever documented in the entire history of modern seismology was one of these waves arriving back at the surface with enough leftover punch to physically move a fault. This isn't new information. What was new, what nobody had ever actually documented before, was the idea that one of these deep, core reflected waves could travel all the way back up to the surface and still carry enough leftover force to trigger something. For decades, the assumption among seismologists was straightforward. Whatever energy made that entire 3,600-mile round trip down to the core and back would have been thoroughly scattered, weakened, and dissipated along the way. By the time it reached the surface again, there simply shouldn't be enough left in that wave to do anything meaningful at all. It would arrive as a faint, spent echo, interesting to a physicist studying how energy travels through the deep earth, but not powerful enough to actually move anything. The earthquake that put that assumption to the test happened on March 11, 2011, off the coast of the Tohoku region of Japan. A magnitude 9.0 rupture, one of the 5 strongest earthquakes ever measured anywhere on the planet since modern seismographs existed. To put a magnitude 9 into perspective, the seismic scale is logarithmic, which means each whole number represents roughly 32 times more energy released than the number below it. A magnitude 9 earthquake doesn't just feel a little stronger than a magnitude 7. It unleashes over 1,000 times more energy. Only a handful of earthquakes in the entire era of modern instrumentation have ever reached that magnitude 9 threshold at all. The 1960 Valdivia earthquake in Chile, still the largest ever recorded, the 1964 Alaska earthquake, and the 2004 earthquake off Sumatra that triggered the Indian Ocean tsunami. Tohoku joined that exclusive, terrifying list. The quake itself, combined with the tsunami it unleashed, killed roughly 20,000 people and triggered the Fukushima nuclear disaster, cementing March. Immediately, one of the most exhaustively studied seismic events in scientific history. Hundreds of research papers poured out in the months and years that followed, examining nearly every angle of what had happened. And yet, buried inside that mountain of meticulously recorded data, one small, persistent anomaly kept bothering a geophysicist named Sun-Young Park, an assistant professor at the University of Chicago. Years after the initial disaster, long after most of the obvious scientific questions about the Tohoku earthquake had already been answered, Park kept coming back to a strange wiggle in the GPS records, a sudden eastward shift, registered simultaneously by monitoring stations scattered across the entire country, occurring about 16 minutes after the main quake, but before the major aftershocks that followed. It didn't line up with any known aftershock. It didn't line up with any documented slow slip event, the kind of gradual, silent fault movement that sometimes happens without generating a noticeable jolt. And most strikingly, it wasn't localized to one region near the epicenter, the way you'd expect an aftershock's effects to be. It was uniform. The same shift, at the same moment, recorded by stations spread across nearly 2,000 miles of Japanese coastline. Most of the time, we would see an offset like this when there's actual earthquake happening, Park would later explain. But here, there was no known aftershock at this time, so we were quite curious. That curiosity turned into years of painstaking detective work. Working alongside Hiru Kanamori, one of the most respected seismologists in the world, based at Caltech, and Luis Rivera of the University of Strasbourg in France, Park began systematically ruling out every plausible explanation. Could it have been an undersea landslide? Some sudden collapse of sediment on the ocean floor sending a jolt through the crust? The data didn't fit. A landslide would have produced a far more localized effect, concentrated near wherever the collapse occurred. Not a uniform shift, registered simultaneously across the entire length of the country. Could it have been a slow slip along one of the region's many fault lines, the kind of quiet, gradual fault movement seismologists sometimes detect without any accompanying violent shaking? That didn't fit the data either. The timing, the uniformity, and the sheer geographic scale simply didn't match what a slow slip event typically looks like. What was left, once every conventional explanation had been eliminated, was something almost nobody had considered as a real possibility. That the strange shift wasn't a new, independent seismic event at all, it was an aftershock of a completely different kind. not a rupture that occurred somewhere nearby on the fault, but the delayed, returning echo of the original earthquake itself, an enormous wave of seismic energy that had raced downward from the initial rupture, traveled roughly 1,800 miles straight down to the boundary of Earth's liquid outer core, reflected off that boundary the way an image bounces off a mirror, and then traveled the same 1,800 miles back up to the surface. A round trip of roughly 3,600 miles, completed in right around 15 minutes, confirming that theory required combining two completely different kinds of instrumentation that don't normally get compared side by side in this way. Traditional seismometers measure the shaking of the ground directly, how fast, how hard, and in which direction the Earth is vibrating at any given instant, which makes them extraordinarily good at capturing the sharp, sudden jolt of an earthquake or an aftershock as it happens. GPS stations measure something different, not vibration, but position, precisely where a fixed point on the Earth's surface actually sits, moment to moment, relative to a global reference frame of orbiting satellites. A GPS station won't necessarily catch the violent shake of a passing wave the way a seismometer will, but it will catch something a seismometer might miss entirely. A slow, quiet, but permanent shift in where the ground ends up sitting once everything settles down. By laying the GPS position data and the seismic shaking data from the same stations directly on top of each other and watching how they lined up in time, Park's team could see something neither dataset alone would have revealed. A slow, coordinated eastward creep that showed no accompanying violent shake at all, exactly the signature you'd expect from a wave that had traveled far enough and been altered enough to lose its sharp, sudden character while still retaining enough underlying force to nudge the fault. And when that wave finally arrived back at the surface, it apparently still carried enough force to do something seismologists had never before documented. It reactivated the fault zone around the original rupture and triggered fresh slip along two entirely separate major tectonic plate boundaries elsewhere across Japan, one at the intersection of the Pacific and Okhotsk Plate, S, the other along the boundary between the Philippine Sea and Eurasian plates. In other words, an echo of the original earthquake bounced off the literal core of the planet, came back up, and physically moved plates that the original quake itself had not directly ruptured. Let that sink in for a moment, because this is the detail that turns this from an interesting footnote into a genuine paradigm shift. The total displacement was small. The entire island of Japan moved permanently eastward by roughly 5 to 6 millimeters, an amount you would never feel standing on solid ground, an amount smaller than the width of a standard pencil. But the sheer scale over which that displacement occurred is what makes this the broadest seismic event ever documented, stretching across roughly 1,800 miles of Japanese territory, releasing an amount of energy roughly equivalent to a magnitude 7.5 earthquake, all triggered not by fresh rupture at the fault, but by a wave that had already traveled to the center of the planet and back. Why did it take 15 years for anyone to notice something this significant? Partly, it's a matter of instrumentation and expectation. Seismic sensors are generally engineered and calibrated to detect the short, sharp, high-frequency vibrations that accompany a typical earthquake or aftershock, the kind of rapid shaking most people associate with the ground actually moving beneath their feet. A slow, broad, delayed shift like this one doesn't announce itself the same way. It doesn't produce a dramatic spike on a seismograph. It shows up, if it shows up at all, as a subtle, gradual offset buried inside GPS positioning data, precisely the kind of signal that's trivially easy to write off as instrument drift, atmospheric interference, or simple noise, especially in the immediate aftermath of one of the most chaotic natural disasters in modern history. There was also a ton of noise going on in the aftermath of the 9.0 quake, Park explained. It took comparing both GPS positioning data and seismic recordings side by side across every available station in the country before violent shaking from the initial 9.0 rupture likely weakened the surrounding plate boundaries, loosening the rock enough that when the deep, core-reflected wave finally arrived back at the surface 15 minutes later, it found faults that were, in a sense, already primed to slip. In Park's words, this indicates that large earthquakes can influence a fault even after the main shaking is technically over, that the danger from a truly massive earthquake doesn't necessarily end the moment the ground stops visibly moving. There may be a second act, arriving minutes later, born from an echo of the very same event, striking not necessarily at the original rupture site, but potentially at plate boundaries considerable distances away. That's not a small detail for the people whose job it is to forecast and prepare for seismic hazards. Every model currently used to assess earthquake risk is built around a fairly straightforward premise. The fault ruptures, energy releases, aftershocks follow in the surrounding area as the crust settles, and the immediate danger from that specific event gradually tapers off from there. This discovery adds an entirely new variable to that premise, a delayed, deep, core-reflected pulse of energy that can apparently reactivate faults and trigger fresh slip on plate boundaries. The original rupture never directly touched, arriving on a predictable, roughly 15-minute delay after the largest quakes. As Park put it herself, this is adding an entirely new angle of seismic hazard scientists didn't know about before. It doesn't mean every major earthquake produces a phenomenon like this. This appears to be the first time anything like it has ever been conclusively documented, out of every large earthquake modern instrumentation has ever recorded. But it means the list of things seismologists need to watch for in the minutes following a truly massive quake just grew by one previously unimaginable entry. There's a strange silver lining buried inside that unsettling discovery, though, and it comes down to timing. 15 minutes is not nothing. In the world of earthquake early warning systems, 15 minutes is an eternity. Entire evacuation protocols, infrastructure shutdowns, and emergency broadcasts are built around warning windows measured in seconds, sometimes tens of seconds, between the moment a quake is detected and the moment its worst shaking arrives somewhere else. A phenomenon with a predictable, physics-based delay of roughly 15 minutes, the time it takes a wave to travel down to the core, reflect, and travel. Back up is, at least in principle, something a warning system could actually be built around. Once scientists better understand which large earthquakes are prone to producing this kind of delayed core-reflected pulse in the first place. That's still a long way off. This is, after all, the first documented instance of the phenomenon happening at all, and researchers don't yet know how to predict when it will occur or exactly which plate boundaries it might reactivate. But the mere existence of a measurable, physics-based delay window, rather than a random or instantaneous trigger, is exactly the kind of detail that earthquake engineers spend careers hunting for. There's also something almost poetic buried inside the mechanics of this discovery, if you sit with it for a moment. For the wave to have made any difference at all, it first had to survive a journey that physics said should have destroyed it, plunging down through roughly 1,800 miles of increasingly hot, increasingly pressurized rock, striking a boundary where solid mantle gives way to an ocean of liquid iron and nickel churning at temperatures hotter than the surface of the sun, reflecting off that boundary, and then climbing back up through that same crushing 1,800 miles of rock a second time, and somehow, against every expectation, it arrived back at the surface still carrying enough coherent force to move solid ground. To grasp just how extreme that environment actually is, picture standing at the mantle core boundary itself, roughly 1,800 miles beneath your feet right now. Temperatures there climb to somewhere around 4,000 degrees Celsius. Hot enough to vaporize almost anything found on the surface of the planet instantly. Hotter, in fact, than the surface of the sun itself. Pressures at that depth exceed 1,000,000 atmospheres, a crushing force equivalent to stacking the weight of dozens of aircraft carriers onto a single square inch. And the outer core itself isn't solid rock at all. It's a vast, churning ocean of liquid iron and nickel, constantly flowing and swirling in patterns that generate the entire magnetic field, shielding our planet from the sun's radiation. That boundary between the rigid mantle above and the flowing metal ocean below is one of the most extreme environments this planet has to offer, and it's the same boundary that Inge Lehmann first proved existed using nothing more than the careful analysis of seismic waves nearly a century ago. Seismologists had modeled this kind of reflection for decades in the abstract, confident the energy would simply be too diminished by the return trip to matter. Japan's earthquake, and the sheer density of instrumentation blanketing the country, finally gave the physical world a chance to prove that assumption wrong. It raises an obvious, unsettling question that Park and her colleagues are careful to leave open, rather than answer definitively. If this phenomenon went undetected for 15 years inside data from arguably the most closely monitored earthquake in human history, how many other major earthquakes in less densely instrumented parts of the world might have produced the exact same kind of delayed, core-reflected aftershock with nobody ever noticing it happened at all? Every large earthquake since modern GPS monitoring began is now in a sense worth a second look. Not for the shaking everyone already documented in the first few minutes, but for whatever quiet, uniform, easily dismissed wiggle might be sitting forgotten in the data 15 or 20 minutes later, waiting for someone patient enough and stubborn enough to notice it doesn't fit. Think about how few places on Earth could even produce the evidence needed to catch this in the first place. Chile's 1960 quake, still the largest ever recorded, struck decades before GPS satellites existed at all. The 2004 earthquake off Sumatra, despite its catastrophic scale, occurred in a region with nowhere near the density of monitoring stations blanketing Japan. Of the handful of magnitude 9+ earthquakes ever recorded by modern instruments, Tohoku may be the only one that happened in a place equipped precisely enough, with a network dense enough, to catch a 5mm shift spread across an entire country and distinguish it from noise. which means this discovery may not just be rare because the phenomenon itself is rare. It may be rare because Japan was, for a long time, the only place on Earth capable of proving it happened at all. That patience is really the heart of this whole story. Sun Young Park didn't stumble across this discovery by being in the right place with a new instrument pointed in the right direction. She found it by refusing to let go of a small, inconvenient anomaly that everyone else had already filed away as noise, a 16-minute-old wiggle in 15-year-old data that most researchers would have every reasonable justification to ignore. It took years of comparing datasets, ruling out explanation after explanation before what was left standing was something that had never been documented before in the entire history of seismology. An earthquake's echo bounced off the liquid heart of our planet, arriving back at the surface with enough force left to permanently move a country. Consider, for a moment, what that says about the current state of a science most of us assume was settled decades ago. Plate tectonics is one of the great triumphs of 20th century geology. A theory so successful, so thoroughly confirmed by generations of evidence, that it now gets taught to schoolchildren as simple, settled fact. Continents drift, plates collide, earthquakes happen at their edges, and the ground eventually goes still again. And by and large, that picture holds up remarkably well. But buried inside data from the most exhaustively studied earthquake of the 21st century, an event that had already been the subject of hundreds of published papers, examined from nearly every conceivable angle by some of the best equipped seismologists on the planet, there was still a phenomenon nobody had thought to look for, hiding in plain sight for a decade and a half. Not because the data was hidden or the instruments were inadequate, but simply because nobody had yet asked the right question of it. That's a humbling thing for an entire field to confront, that even its best documented, most thoroughly dissected case study still had one more secret left to give up, waiting patiently for someone to notice a wiggle that didn't quite fit. The ground we stand on, it turns out, doesn't just shake once and go quiet. Sometimes, 15 minutes later, it's still listening to what happened, sending a message down to the core of the planet and waiting to see what comes back. On March 11th, 2011, it got its answer, and the entire island of Japan quietly, permanently moved because of it. And for 15 years, almost nobody on Earth knew it had happened at all.